Hi, it's Kevin Lobates here, and today I thought it would be fun to make a video about how we stop the replaying of transactions in blockchain. So there's a bit to unpack in that statement, and maybe the best thing to do is to start off with a high-level description of how transactions work. And a transaction consists basically of two parts. The first part is a command to do something. For example, to move some quantity of a digital asset from an address that I control to someone else's address. Now, to prevent anybody from issuing such a command, and therefore making the whole principle of blockchains useless, a command in a transaction has to be digitally signed. And it has to be digitally signed with the private key that the blockchain address is derived from. So I have a private key. Using that private key, I can generate a public key. From the public key, I can generate a blockchain address, and the blockchain address has some digital assets registered against it. For example, on Ethereum, it may have a balance of Ether, it could have a balance of USDC and things like that. And that means that on the Ethereum blockchain, somewhere in the data for the blockchain, there's a bit of some numbers registered against my blockchain address saying exactly what my balances are. And then when I issue a command to transfer some of those balances, I digitally sign it using a digital signing algorithm and my private key, and that digital signature contains my public key and verifiable data that shows that I did indeed sign the command. And that's what authorizes the command, and that's what the blockchain nodes then use to go ahead and execute the command, for example, by decreasing my balance of Ether and increasing some other addresses balance in accordance with that. And there is a problem in blockchains, namely that if you just had that for your transaction, then you could have the situation where people could copy my transaction and submit it again. And so if I had 100 USDC registered against my blockchain address and I transferred $1 from my address to my friend's address, other people could copy that transaction and its signature and submit it again and again. And as a result, although they wouldn't benefit from it, they would cause all my $100 to be transferred to my friend's address. And of course, if I've transferred $1 to somebody I don't know, then they could replay my transaction and transfer all my USDC to their address. And Ethereum uses one particular solution to this problem, which is to require that each transaction has a sequence number in it. It's also called a number used only once, or a nonce. And the principle is that for each address, each transaction has to have a sequence number, and each transaction has to have a sequence number that is one higher than the one that went before it. So my first transaction is given a sequence number of 1, and then my next transaction is given a sequence number of 2, and so on. So if I submit my first transaction with a sequence number of 1 to transfer that 1 USDC to some other address, if people try to replay it, the nodes notice that it has the same sequence number as a transaction that has already been executed, and therefore they refuse to repeat the transaction again. And as a result, if you have an Ethereum address and you've executed 10 transactions, you'll be at sequence number 10, and your next transaction should have sequence number 11. Now, this does bring some advantages and some disadvantages with it. The disadvantage is that if I submit, say, transaction number 9 and then transaction number 10, and transaction number 9 gets hung up for some reason, for example, I haven't paid enough gas, then transaction 10 won't execute because the transactions have to be executed in sequence. And as a result, you can end up with things getting stuck. You're waiting for the 9th transaction to clear before it'll go ahead and do transaction 10. And there are ways around solving this. If your problem is you haven't paid enough gas, you can submit another transaction with sequence number 9 paying more gas, and that encourages the validators on Ethereum to then pick up that transaction and execute it, and then 10 will be done. And in fact, this illustrates one of the advantages of the system, which is provided you're fast enough, you can countermand a transaction that you submitted. Let's say I accidentally mistyped and I transferred, or rather I submitted a transaction to transfer 100 USDC instead of 1 USDC, which is what I wanted. Well, I can quickly submit another transaction with the same sequence number and then pay a bit more gas for it, and economics suggests that the validators will then pick up that transaction instead of the lower gas one and execute that one instead, as long as I'm fast enough and the previous one hasn't already gone through. And that way I can avoid the transaction I didn't want to happen in hindsight from going through. But it's a bit touch and go. You have to be fast, and you have to hope that the validators are aware, get your transaction quickly enough, and make the economic decision to pick the one that will pay them more in gas fees than your original one. So sequence numbers are one solution to preventing transaction replays. Another solution is the one that is used on Bitcoin, which is that Bitcoin doesn't actually have balances registered against addresses as such. It uses this thing called unspent transaction inputs and outputs. And there, well, it's a bit tricky to explain, but the idea is that Bitcoin doesn't document balances, it documents flows of balances. And if I have a Bitcoin address with a balance of 1 Bitcoin, what I actually have is a Bitcoin address with an unspent transaction input of 1 Bitcoin. And that's got a distinct identity on the blockchain. And if I then try to spend, say, half a Bitcoin, transfer half a Bitcoin to somebody else, my wallet takes that 1 Bitcoin unspent transaction, turns it into a new transaction going to the new address containing half a Bitcoin, and a new other half Bitcoin transaction going back to my original address, or if you're following Satoshi Nakamoto's original design, to a new change address, which I can then use for further transactions. And when you want to submit particular amounts of Bitcoin to people, your wallet goes through and looks at all these different unspent transactions and groups them up into ideal ones to recombine them into a new flow, into a new address. As I said, it's a bit complicated. There are books and articles out there that explain it in better detail than I can walking through the forest with a camera in front of my face. But as I said, it boils down to the fact that you're documenting flows of assets rather than balances. So a real problem in blockchain, and one that is solved through, at the moment, one of these two solutions. This gives rise to a further problem that you have in blockchain, which is that there are lots of different blockchains out there that are forks or in a kind of clones of other existing blockchains. And so you can have the problem where a transaction on one chain could then be replayed on another chain. And again, Ethereum has a solution for this, which is that every transaction has to have a chain ID. Each Ethereum-like chain has an identity, and the chains in aggregate have agreed to follow this policy. It's all coded into the Ethereum nodes, and therefore when someone spins off a fork of Ethereum, they end up picking this up too. And you can actually go and look up the identifiers for all the chains out there. There's a site called chainlist.org where people register them these days. And the idea there is that if I have a transaction that I've submitted on Ethereum, it'll have in the transaction the ID of the Ethereum chain, which happens to be 1. And then if I take that transaction and try to submit it to another chain, it'll get rejected by that chain's nodes because the ID for that chain might be 120 or 1134 or something like that. And the nodes will spot that, hey, this is for chain 1. That's an Ethereum transaction. That's not a transaction for this chain. This was a real problem in Bitcoin when Bitcoin Cash and then Bitcoin Stephen Vision forked off, because Bitcoin Cash and Bitcoin Stephen Vision decided not to have separate IDs, and as a result, at the point of the fork, the Bitcoin Cash and the BSV chains were identical, and there was no way to tell whether a transaction was for the former or the latter. And as a result, when you transferred Bitcoin Cash, people could submit that transaction to the other chain and it would execute there too. Eventually the two chains diverged, and then transactions submitted on one chain could not be replicated on the other because too many things, underlying things, had changed. However, if you are trying to transact with Bitcoin Cash or Bitcoin SV from before the fork, you have to be very careful to ensure that your transaction cannot be replayed on the other chain. I've got a bunch of stuff about this in my book, Move Over Brokers, Here Comes the Blockchain. There's a whole chapter, or rather a whole section of a chapter on this replay problem. So I'll put a link at the bottom of the video. If you're more interested in this topic, I have some clearer explanations on paper with some analogies to explain exactly what's going on there. Anyway, I think I've been talking for far too long, so I'm going to wrap up this video now, but I hope you found it an interesting walk through the concepts of blockchain transactions and some of the problems that maybe some of you haven't thought about that blockchains have faced, and that fortunately for you, they have, generally speaking, solved. I hope you found this interesting, and I'll see you in the next video soon. Bye for now.